All right, our final example here for geometric distributions. Determine the probability of rolling a sum of 10 in fewer than 5 rolls on a pair of die. Okay, this is one of those things that I've mentioned earlier. It's not desirable, but we need to be able to deal with it. On the previous example, it said her fourth shot. So it was exactly on her fourth shot, not less, not more. As soon as you see that term at least or fewer or more than, that's when it is necessary to go into that tabular form to make the calculations, because this means that fewer than five rolls, that means 1 roll, 2, 3, 4, 5. So we need to know the probability of 1 through 4. So we quickly set up our chart. Again, it's going to be waiting times for our x value. So waiting times. And here is our independent random variable, the resulting probability. So over here, if I want to do it on my first roll, I would have a 0 waiting time. Second roll would be 1 waiting time. 2, 3 rolls, and our fourth roll would be 3 waiting times. So fewer than 5. So that excludes 5 from the calculation. So I'm looking at 1 through 4 rolls, which means I'm looking 0 through 3 in terms of our waiting times with the distribution. Okay, so you're asking yourself, well, how do I know this is not binomial? Okay, it is determine the probability of rolling a sum in fewer than 5 rolls. So we're looking at waiting time, probability of waiting that long to have that success. All right, so the formula off to the side here, a sum of 10. Quickly bringing out my dice chart, and this is something, again, you want to have handy. Just pull that out just like that. You can easily do that with your notebook, obviously. Just go to the sidebar and bring it on in. So a 10, 1, 2, 3. Okay, there are 3 possibilities. So that means that my success here is rolling a 10, so a 3 in 36 chance. Failure is not being able to roll that 10, so it'd be a 33 and 36 chance. So setting it up, we are looking at failing, and I'll do it for the first example. Anything to the exponent 0 is just a 1, so it's not necessary to write that in. But this is what it ends up looking like. 33 to 36 squared. And once you have it set up, it's just an exercise in using your calculator. So 3 and 36. And it's always to the exponent 1 because it's the last event that happened. It is your success. So, pulling out the old calculator, quickly running through it. The first one's a 3 and 36, but let's work with decimals here. Oops, not 80%. Pull that back a little bit. 0.83 and 30 over 36 times the 3 over 36, 0.069. The 33 over 36. Take that to the exponent 2 and multiply by 3 over 36. And I'm not sure what I'm actually doing here in terms of with the calculator. Notice that I'm just multiplying by another 33 over 36. So I'm just take my 0.07 now, rather than punching it all in, and multiply by a 33 over 36. Just a minor brain cramp, which is somewhat normal. So 0.64. And just want to double check that, but assuming the calculations are correct there, all that's left then is to add that up. So the 0.083, that middle one is still bothering me, but let's just double check it. 0.076, yeah, I did make a calculation mistake, sorry about that, people. 0.076. I just noticed that it jumped back and forth. It didn't make a whole lot of sense. Common sense would say that it's got to start high and then decrease every time. So, and remember, the reason it's decreasing every time, one more time so you understand this, the reason that probability is decreasing with each roll is that we're approaching that expected number of rolls to have a success. So the longer you wait, the higher the success should be. It should be a greater chance of occurring, so keep that in mind. So it is getting lower and lower, closer to 0% chance that you have to wait that long. Anyhow, just going to add up these 4 numbers down the side because this is an at least question, so that means we have to add them up. So 6, see if I can do that properly. 0.064, so 0.293. So therefore, to answer the question, probability of waiting 3 times or having success in the first 5 rules is 29.3%. Okay, so that tells me that if I'm going to roll a 10 using the dice, there is a 29% chance that I'm going to do it in the first 4 rules. All right, and that's what that means. So there's the homework with geometric distributions. Good luck. If you have any questions, please feel free to ask.